Okay, so this is recitation problems, recitation 2, problem number 4. In this problem, right, we have a laser light hitting some material. It's coming at an angle, and I'm going to change these angles around, and you have a laser light. So here is a laser light beam, a laser beam coming in, hitting the surface of some material. We don't know what the material is. So whatever the material is, it's coming from air. So this is air. And the material, I don't know. So let's call it N question mark. And let's say that the incident angle is given as theta is 30. Let's make it 45 degrees. I'm sorry, I'm making up these numbers, but I don't want to use the numbers from the recitation. So we have a laser firing into a material. So here is coming in at an angle of 45 degrees. So this is theta 1. So this is N1. We know the index of air, right, is 1.0, roughly vacuum, right? Because air does not interact with laser light or any light, and so effectively. We're also told that the laser light, let's make it, actually I don't want to use the same numbers, so let's imagine that the laser light, right, has a wavelength of, let's make it 550 nanometers. Okay, so if you're wondering, visible light, right, is roughly about 480 nanometers all the way up to about 730 nanometers, roughly. Red light is 730 nanometers, something around there. So it's 550 is give or take. It's roughly in the visible light, so we can actually see this light beam. So we have a laser light coming in 45 degrees. And saying that when it exits, right, let's assume that theta 2 happens to be 30 degrees. So there's not exactly the same numbers. So one is coming in 45 degrees and the other one is N2. And the question is, can I find the index N? Now, before you solve this problem, right, you should ask yourself, right, what's the light doing? I can apply Snell's law, which is N1 sine theta 1 is equal to N2 sine of theta 2. And we can solve for N2. That's what, here's N2. But before you do it, you should actually take a look and ask yourself, what's the light ray doing? It's coming in and it's bending into the material. And we said qualitatively, whenever you look at Snell's law, right, we should think of it as, it's a statement that whenever light hits interfaces, it tends to bend into the material that has the highest index refraction. So if this was a larger angle, right, so it's 30 degrees is actually very deep, it's going into the material, so N2 must have a higher index than air. Well, we're expecting that, right, because that is air, after all. It is anything, it's going to interact with the material much more readily. The laser light is going to interact with the material more readily than air, because air is like really, particles are really far apart. But what if this was like 50 degrees? So 45 degrees, it bends slightly into bending this way. So we're expecting a straight line and then it's bending this way instead. Well, it's trying to get back into this material, and if it is, that means that the index refraction of this material is actually higher than the index refraction is. But of course it's bending into, because we know this is air. Air, you can't get smaller than a 1.0 for index refraction, because light travels at the fastest in vacuum, and air is slightly a little bit slower, but so we can't actually go faster than the speed of light. Okay, so let's go and plug this in and try to find the index refraction. So N2, and divide into here, so this is N1 sine of theta 1 divisible by sine of theta 2. And so N2 is given by 1.0 times sine of theta 1, all divisible by sine of 30 degrees. So plug into your calculator and you get yourself a number, an index refraction. So remember, really I chose sine of 45 because I hope some of you might recognize sine of 45 is 1 over square root 2, but plug into a calculator. and sine of 30 is a half, and so you should be able to get a quick answer. Anyway, I actually won't go through it, but this is the index refraction of material N2. Now, we're also asked, right, if you're given lambda is 550 nanometers, right? Actually, this is kind of really problematic because it's not really emphasized enough in your textbooks. Whenever light or any kind of wave, right, hits material, the frequency never changes. That's kind of really strange. So if frequency doesn't change, right? Actually, you know, I won't mention it any further. I'll just say frequency doesn't change, and I was going to go through the details and everything. But in air, right, you're given lambda, and then you're actually asked to find the frequency of the light in air. And the frequency of the light, you have to remember that lambda times frequency is equal to the speed of light in air. And I think that was the problem, right? Frequency and speed in solution. Oh, actually, I'm sorry. We also, so once we calculate N2, we have to calculate the speed of the light in the material. And I'll do that after I calculate lambda times f and calculate the frequency in the air. So the frequency of the light in the air is given by c over lambda, because c is the speed of light in vacuum, which is approximately that of air. So this is 3.0 times 10 to the 8 meters per second. Standard units is, let's see, 550 nanometers, so 550 times 10. A nanometer is minus 9, so this is meters. So we can get rid of the meters, and we can actually plug this in. 2 significant digits, because actually I can do it now, but I hope I'm really emphasizing using calculators, so might as well. Divided by 3.0 exponent to the 8 divisible by 550 exponent to the 9 minus gives me a 5.5 times, it's actually 5.45, but I'm rounding it up, so 5.5 times 10 to the 14 hertz. Okay? And anyway, so that's the frequency of light. We're also asked that if you're given this N2 index, right? Actually, so let me calculate this. So I'm typing in 1.0 multiplied by 45 sine divisible by 30 sine is equal to 1.4. Index of refraction is 1.4. And if you remember earlier, right, if you're given an index of refraction, we can actually calculate the speed that the light is traveling inside the material. So if you remember, n is equal to c divisible by the speed of the material, the light traveling in that material. We solve for v, so v is equal to c divisible by n. In this case, c is 3.0 times 10 to the 8 meters per second. Index refraction is 1.4, and so let's plug it in. 3.0 divisible by 1.4 equals, so we get 2.1 times 10 to the 8 meters per second. So in this example, it's not the exact solution, but none of the videos that I'm making, right, will have exact recitation problems. They'll be slightly different with numbers and stuff, but basically the general solution. So what you should have learned, right, is to remind you that lambda times frequency is equal to c. And remember, this equation, right, is nothing more than saying that you have a wave that's traveling, so the wavelength is defined to be here, and this wavelength, right, lambda, so this is actually an equation that says distance traveled over the time taken, which is time taken is the velocity of the object. But distance, right, is lambda, and 1 over t is frequency. So remember, this is really the statement of a wave is really a statement, right, of distance divided by time is actually equal to the speed of the object traveling. So it's kind of a little messy in here, but So kind of review also Snell's law. So it's a mixture of Snell's law and your view of lambda times f is equal to c.